everyone. My name is Mark Hildebrand. I am a PhD student at the University of California, Davis, and today I'll be presenting our work on AutoTM. So what exactly is AutoTM? Well, AutoTM is a technique for optimally managing the placement and movement of intermediate data in the form of tensors to facilitate the training of very large deep neural networks on a single device. Our general idea is that we can use profile-guided optimization to understand the impact of multiple memories on kernel performance, and that we can model this tensor assignment problem as an integer linear program. Some key results we have is that we found we can replace 50 to 80% of a system's DRAM with slower memory, such as non-volatile DIMMs, and only lose about 20% of performance, even though the devices that were, the NVDIMMs themselves, are much slower. Furthermore, we found that our intelligent software technique can perform up to 3 times faster than a real hardware caching mechanism found in state-of-the-art Intel processors. So here's a little overview of what I'm going to talk about. I'm going to give some motivation and background on this problem. Then I'll talk about how AutoTM works and give some high-level details. Then I'll talk about how we implemented AutoTM on a real system and share some results from the system, and then we'll wrap up with a few concluding remarks. By this point, deep neural networks don't really need any introduction. They've become ubiquitous in computing and have seen use in all areas. Recently, the trend has been towards using ever larger and more complicated networks. For example, Microsoft recently introduced a language model called Turing NLG that has 17 billion parameters. Now, these larger models are starting to greatly exceed the amount of memory available to a single device and require practitioners to distribute training across multiple devices. The question we want to ask is, can we use multiple levels of memory, potentially using a slower but larger capacity memory, to train these large models on a single machine? So what do we mean when we say heterogeneous memory systems? For this work, we consider systems with 2 types of memory: a fast memory that is expensive but limited in size, such as DRAM, and a slower memory that is cheaper and has higher capacity. For this work, we use Intel Optane DC persistent memory modules as our larger capacity memory. These non-volatile DIMMs, or NVDIMMs, sit right next to the DRAM DIMMs on the CPU motherboard and are both controlled by the same memory controller. This means that the CPU can write natively to both devices with a byte-level granularity, and there's no operating system overhead of writing to these NVDIMMs. It's worth noting that we're using NVDIMMs just for their higher capacity and lower cost in this work. We aren't using them for the persistent capability. So what are some challenges associated with using this style of memory? Well, we found that just placing all tensors naively into the NVDIMMs is far too slow, with a performance impact of 5 to 8%, or 5 to 8 times over just using DRAM. Now, these CPUs have a caching mechanism where the DRAM is used as a cache for NVDIMMs, but we will show later that we can greatly outperform this cache using intelligent software managed techniques. All right, so now I'll go into some of the details about how AutoTM works. AutoTM is built on top of the ngraph compiler, and in this compiler framework, neural networks are modeled as directed acyclic graphs, such as this shown on the slide here. The nodes in the graph are compute kernels, so this could be convolutions, poolings, activations, etc. And the edges between the graph represent tensors that model the data movement between kernels. The goal of AutoTM is to minimize the execution time of this computation graph with some constraint or some size constraint on fast memory. How does it do this? Well, it places tensor in slow memory and fast memory optimally, and also schedules the movement of tensors between these different memory pools to minimize runtime. And our strategy here is to profile the performance of these kernels with their various inputs and outputs in DRAM and persistent memory, and then model this tensor assignment problem as an integer linear program. So let's talk about profiling for a little bit. The goal of profiling is to take all of the input and output tensors for each kernel and measure the performance of that kernel under all memory locations of those input and output tensors. For example, kernel K2 in this computation graph has 1 input tensor and 2 output tensors for a total number of 3 input-output tensors. With 2 levels of memory, that's DRAM and persistent memory, this gives a total number of 8 different combinations of input and output locations that we have to profile. Now, why is this important? Well, this graph in the lower right shows the performance of a convolution kernel with its various inputs and outputs in different memory locations. What we observe is that the performance of this kernel is very sensitive to the location of its data output, running several times slower when it's outputting data directly into persistent memory. However, the performance of this kernel is not particularly sensitive to the location of its input data and wait inputs. The performance of kernels and the relative slowdown you see varies depending on the exact data use pattern of each kernel, so we have to do this profiling for every single kernel in the graph. Next, I'll describe how we model this as an integer linear program. One of the key transformations that we do is for each tensor in the computation graph, we create a tensor lifetime flow network. Well, what's shown on the slide is the tensor lifetime flow network for tensor T1 in this computation graph. For each kernel that uses tensor T1, we create a component in the graph. Now, this flow network has a single source on the far left and a single sink on the far right. All other nodes in the graph simply conserve flow. And then for each component in the graph, we also have a persistent memory decision node and a DRAM decision node. The idea here is that flow is either going to go through the persistent memory node or the DRAM node, and that will describe which memory pool the tensor will be in at that point in the computation graph. Furthermore, we have move locations that describe when the tensor is going to move from persistent memory to DRAM or back. So the path of flow through this graph describes all the locations the tensor is going to be at during its lifetime. We create one of these flow networks for every tensor in the computation graph, and then we use this to build the rest of the mathematical model. Remember, our objective here is to minimize the expected computation time of this computation graph. So for this formulation, our objective is broken up into 2 parts, as you can see on the slide. The first part is the expected kernel execution time. And to see what we mean by that, I'll give an example for kernel K2. So suppose we wanted to find the expected execution time of kernel K2. What we would do is look at the region of the flow networks for all the tensors that are in input or output for kernel K2. And by investigating the flow network, we can determine the location of all of the input and output tensors, whether they be in persistent memory or DRAM. And then using that information and the information we got from profiling earlier, we can determine the expected execution time of the kernel. And then we can do this for every kernel in the graph. Second, we have to include tensor movement time. In this particular formulation, tensor movement blocks computation, and so we have to add it on separately. If we wanted to compute the amount of time that we spend moving tensor T1, for example, all we do is look at all the portions in its flow network where it moves between memory pools, and then add up the expected time for each movement. Finally, we get to how do we set a limit on the amount of DRAM that we can use? Well, again, we look at these flow networks, and for each kernel, we can determine which tensors are in DRAM as well as the sizes of each of those tensors. And we can sum up all of that information and set that to be less than some particular limit. And if we apply this for all kernels, then we'll have effectively a limit on the amount of DRAM used. So in conclusion, we're trying to minimize the computation time, which is composed of kernel execution time and tensor movement, and we have a constraint on the amount of DRAM available to the application. So what I just presented was the synchronous formulation of AutoTM. In this formulation, tensors are allowed to move between persistent memory and DRAM and back, but that tensor movement blocks computation. That is, it's not overlapped with kernel execution. We have two other variations of AutoTM. We have the static variation, where tensors are not allowed to move between memory pools. They are either produced directly into persistent memory and stay there, or produced directly into DRAM and stay there. And we also have an asynchronous formulation that allows tensor movement to be overlapped concurrently with kernel execution. And we talk more about that in our paper. All right, so now I'll present some results that we had from implementing and running AutoTM on a real hardware system. So as I mentioned, we built AutoTM on top of the ngraph compiler, and that was because it was fairly straightforward to modify the memory behavior of the ngraph compiler, and the static graph semantics of the ngraph compiler were sort of what we were looking for this work. We used Julia's jump package for ILP modeling and Gurobi as our ILP solver. For our hardware, we had a 2-socket Xeon test server with 1.5 terabytes of obtained DC and 380 gigabytes of DRAM. We used 2 different classes of workloads to test this system. Our first class of workloads consists of several popular convolutional neural networks, with the batch size selected such that the memory footprint of these applications was between 100 gigabytes but no larger than 190 gigabytes, which was the amount of DRAM available to a single socket of our test system. What these workloads let us do is artificially vary the amount of DRAM available to the application from the AutoTM side, and compare the performance of reducing the amount of DRAM with the performance of the application using just DRAM. Our second class of workloads consists of the same neural networks, but either deepened, as is the case of VGG 416, or with a larger batch size to get the memory footprint over 650 gigabytes. Now, this means that the model can no longer be trained on a single one of our test systems using only DRAM and must use persistent memory as well. And this lets us compare the performance of AutoTM against Intel's caching mechanism. So as I mentioned, we want to understand the scaling performance of AutoTM. So using AutoTM, we can set an artificial DRAM limit on the application. The ILP will optimize data movement given that DRAM limit and split the data between DRAM and persistent memory in an optimal fashion. So on this graph here, what we have on the y-axis is the slowdown compared to the case where no persistent memory is used. That is, all of our intermediate data is in DRAM. And this implements the fastest possible case that we can run this workload. On the x-axis, we have the DRAM limit provided to AutoTM. And this point on the far right indicates that operating point where all of the data fits in DRAM. So for the case of Inception v4, the maximum memory footprint of the application is 111 gigabytes, so that's the limit that we give to AutoTM. As we can see, we have no performance, we have no slowdown, because this is the all DRAM case, but we also have the largest DRAM footprint, which, if we view DRAM as an expensive material, also incurs the largest cost. On the other end of the spectrum, we have the case where almost all of our intermediate data is put into persistent memory. Now this has the lowest DRAM cost, but comes at an almost 5x slowdown. And this shows that simply using persistent memory naively is far too slow to be acceptable. If instead we investigate the scaling performance of AutoTM, we notice that we can actually get quite a bit of performance back from the all persistent memory case by adding just a small amount of DRAM. For example, with only about 20 gigabytes of DRAM, we are able to come within 20% of the performance of the all DRAM case. So depending on the relative costs of the memories involved, this might end up becoming a cost-effective option. And another thing we notice is that the best performance, this steep curve at the beginning corresponds to the point where all of the input and output tensors for most of the kernels in the computation graph can fit in DRAM while the kernel is executing, and then are moved from the DRAM into the persistent memory before and afterwards. So after we have the steep curve in the graph and we have the longer taper, we're just spending time moving data back and forth. So next, we wanted to compare AutoTM against 2LM. Now, 2LM is a hardware caching mechanism implemented on these Intel processors. And what it does is it uses DRAM as a transparent direct mapped cache for the NVDIMMs. Now, on this graph here, we show the speed up of AutoTM relative to 2LM for these large networks. And what we see is in the worst case, we match the performance of 2LM, but for complicated networks like ResNet 200 or DenseNet 264, we vastly outperform 2LM. A large reason for this is that we can avoid the dirty writebacks that have to happen in the cache because we have some more program semantic information on the lifetime of these tensors. And we also have less memory contention between the DRAM and the persistent memory. And this shows that our intelligent software management technique can outperform this hardware caching mechanism by up to 3 times, which is not insignificant. So now let's go over some concluding remarks. So, of course, AutoTM has some limitations. At the moment, this only works for static computation graphs where we know the order that kernels are going to be executed in and know the lifetimes of all intermediate tensors. Second, we have the kernel profiling overhead, which for large and complicated networks can take some time, though this only has to be done once. And third, we're using ILP as our optimizing mechanism here. And ILP has in some cases, some dubious scaling performances. For our workloads, the solution times were usually on the order of minutes, but in the case of DenseNet, could take up to an hour. Now, we spent very little time optimizing the performance of the ILP, so we're confident that we can reduce this solution time if it ever became a problem. And finally, since ILP is a mathematical way of optimizing nonlinear functions, the solution that comes out of the optimizer might be a little bit hard to understand intuitively. We go into a little bit of work trying to understand this in the paper, though. So in conclusion, we present AutoTM, which is a technique for managing tensors in heterogeneous memory systems. We use profiling to understand kernel performance, and then ILP to optimally do the assignment of tensors. We can greatly reduce the DRAM requirement of applications without sacrificing a large amount of performance, and we perform significantly better than a hardware caching mechanism. Our code is available on GitHub, and we welcome any questions and comments that you might have. All right, so now that the main portion of the talk is over, I'm going to address some common questions that you might have about this work. So first, I mentioned that we had an asynchronous formulation of AutoTM, but we didn't present any results for this on the Optane system. So the reason for this is that we tried to implement this on the Optane system, but ran into some difficulties. First, we used a multi-threaded copy to move the data back and forth between persistent memory and DRAM. This is the technique we found that performed the best. The problem with this, though, is since we need at least a couple of threads to do this data movement, we lose threads from doing computation. And the performance loss from taking these threads from computation was far greater than any performance gain we got back from doing this asynchronous data movement. We spent some time trying to get DMA to work, but found that it had fairly low bandwidth for our purposes. Next, we did actually implement AutoTM on the GPU, and we implemented both the synchronous and the asynchronous formulation. Now, this is a little bit different, or the memory model at least is a little bit different than the Optane system, because the GPU can only access data on its local GDDR, and if we view CPU DRAM as the slow memory, there has to be explicit movement from the CPU DRAM into the GPU DRAM in order for the GPU to actually be able to access this. So yeah, we compared the performance of this against CUDA-malloc managed, which is a more transparent way of managing this data movement, and found that we compared favorably against CUDA-malloc managed. And as we scale the batch size so that the networks no longer fit in the GPU memory, we start to see quite a bit of performance improvement compared to CUDA-malloc managed. We don't see the theoretical peak performance that we can get, just because as we scale the batch size, a lot of intermediate data sizes get so large that we have to use suboptimal execution kernels in CUDNN. And finally, well, there's a question of why don't we present any work for RNNs or more like language models. And that's because at the moment, AutoTM is limited to static computation graphs, and often RNNs or other types of language models have dynamic behavior depending on some input sequence length. And while these RNNs can be implemented statically, doing so will result in a lot of wasted computation in the case where the sequence length is different than your static unrolling of the network. We do think some ideas from AutoTM can be used for these dynamic workloads, and that's what we're looking into next. So again, conclusion, we present AutoTM, and I'm happy to answer any questions that you might have from this work. Thanks for your attention.